Hi, my name is Kelly Carter, and this is my reassessment for Chapter 20. The first question asks us to label the magnitude of the electric field at all parts of the circuit marked with an X. The magnitude of the electric field differs based on the length of the wire and also the cross section. Here, the electric field is a lot shorter in the longer thicker wire compared to here, where the magnitude of the electric field is a lot larger. The reason for this is because the thinner shorter wire can be deemed as a resistor. According to the equation for potential difference, which is the change in potential equals the dot product of the electric field and length of the wire, we can determine that the electric field is shorter. The longer the wire, the smaller the electric field, and the shorter the wire, the larger the electric field. The second question asks us to label the charge distribution also at the locations. Well, as positive charges begin to flow from this side of the battery back into the negative side of the battery, we see a difference in charge distributions. Here, as the charges are flowing out, they remain positive, but once they reach the resistor where the positive charges are trying to get through, the positive charges begin to build up. Electrons are flowing from this side of the battery, which they begin to build up here as they enter the shorter, thinner part of the wire, which is also a resistor. So here, it's not saying that the positive charges, or the protons, are stopping flow. It's saying that here is the excess of protons and here is the excess of electrons. They're continuing to flow and exchange, but the excess differs here as they meet going between the resistors. The third question also asks us to find the electron current that's coming from the negative end of the battery. So the definition of the electron current is I equals NAV. We're given the electron mobility as well as we're given the electron density as well as the electron mobility, which will be U. So in order to find the electron current, we use the equation I equals NAV. The EMF is equal to the change in potential, which is also equal to K, and K is given to us as well. Here, the electron mobility times the electric field will give us the electron motility. And in order to find the electric field, we can find that by the equation for potential difference and doing some rearranging, where the electric field equals the change in potential over L, or the EMF over the length of the wire, which is K over L. We can also find the cross section. We're given the diameter, and the diameter divided by 2 will give us the radius, and so we can also find the cross section. So once you plug everything in, you get the mobile electron density times the cross section, which will be pi d1 squared over 4 for our radius. Multiply that times the electron mobility times K over L, which is our E, and we'll find the electron current. Then it asks us to find it as if it's coming from the battery and it's going straight into the smaller section of the wire. Basically, what we would do is we would just sub in the smaller lengths of the wire, the cross section for the smaller parts of the wire, and also the length. So you will change D1 to D2 and L1 to L2. Thank you.